Hey guys, we're back for the third one on the urinary system, talking about the proximal convoluted tubule. Here it is. Zoom, 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 zoom. And it is proximal to the glomerulus. It's convoluted. Convoluted means really twisty. Twistiness is going to give it a lot of surface area. All right, also give it more time. And this is great because it is the primary site of reabsorption and secretion. The epithelia in here is simple cuboidal, which is good. Simple, one layer, easy to get stuff through. Cuboidal got cells of sufficient size to have a lot of machinery to do the acts of reabsorption secretion. Also, a lot of mitochondria for the energy to power reabsorption secretion. Plus, we have lots of microvilli, which is going to further enhance the surface area. Now, from the proximal convoluted tubule, we get to the loop of Henle. The loop of Henle is going to build a concentration gradient out here, excuse me, in the interstitial fluid of the renal medulla. This is going to be important for later on. It's going to help us, excuse me again, concentrate urine later on. Then we get to the distal convoluted tubule. Distal because it's farther away from the glomerulus. Convoluted because it's twisty. And this is I can't stop clearing my throat here. This is where we do the adjustment, usually controlled by hormones, the adjustment of water and salt secretion and reabsorption so that we can maintain homeostasis. We're still simple cuboidal here, but fewer microvilli and mitochondria, and this is reflective of the fact that we're not doing as much reabsorption and secretion by the time we get over here. All right, then we flow into the collecting duct. Here's a big collecting duct. Remember, about 100,000 of these, while there's about 1,000,000 nephrons. So we're going to have multiple distal convoluted tubules here emptying into the same collecting duct. The collecting duct is going to go through the renal medulla, through the pyramids. They're going to combine and make bigger and bigger ducts, eventually terminating at the renal papilla. Mostly cuboidal and columnar epithelium in here. And we're going to do some final reabsorption of water depending on our hydration levels in the collecting duct. All right, good. So let's go back to that glomerulus, the site of filtration. The glomerular capillaries are different from regular capillaries in two important ways. Two important ways here. Okay, first of all, we got an arteriole going in, afferent arteriole, and arteriole going out, efferent. That's weird. That's not normal. Usually it's arteriole in, venule out. That's the normal sitch, but not here. And there's a big consequence to this. Now look at this awesome drawing I made here. And what's really great about it is it shows you the size differential between the afferent and the efferent. In the real thing, this is an electron micrograph. There's the glomerulus. There's the afferent arteriole. And then there's the skinny little efferent. Notice the big difference in size. So there's more resistance in the efferent than in the afferent. It's easier for blood to get in than for blood to get out. And what this does is it builds up a high blood pressure in the glomerulus. All right, so this differential in size creates high blood pressure here. Maybe it's about 60 millimeters of mercury as opposed to about 25 in a normal capillary. This is important because that high blood pressure drives the process of filtration. All right, let's talk about the other blood vessels we met. We met the peritubular capillaries. They're so named because they're around, around, tubular, the little tubules. They're around the little tubules, the renal tubules. They're going to get blood from the efferent arteriole. They are the sites of reabsorption secretion. Now, the main thing being reabsorbed is water, so the peritubular capillaries have some pressures that are really good at facilitating water reabsorption from the filtrate. The blood pressure in the peritubular capillaries is low. That makes it easier for water to go in. The osmotic pressure of the blood in the peritubular capillaries is high. That makes it easy for water to get sucked in. All right, one more set of capillaries. Down here around the loop of Henle, we have a set of capillaries called the Vasa Recta. Vasa, vessels, recta, straight, because they're kind of straight looking. They're going to help the loop of Henle in its concentration, in its building of a concentration gradient in the renal medulla, which will help us steal water from urine if we need to. Okay, let's review here. 3 big steps of urine formation: filtration at the glomerulus, then reabsorption between the renal tubule and the peritubular capillary, secretion between the same two structures, just going in the opposite direction. So make sure you know all these directions here. All right, good deal. Let's talk a little more about filtration. We know what happens at the glomerulus. We know the glomerulus is a ball of special capillaries with high pressure. And, well, what kind of capillaries are these? Well, look, they've got little holes. What this means is that they are a fenestrated capillary. The little holes make sense because, well, what's happening here? Filtration. And what does filtration depend upon but having little holes? The fenestrated capillary walls are not the only filtering devices, though. This is our podocyte. Remember, the visceral layer of the glomerular capsule is made up of cells called podocytes. Here's the body of the podocyte. And look, he's got all these feet that stick out of him, and the feet have feet. And notice how the feet and the feet of the feet interdigitate, yielding just little small spaces, slits for filtration. And only little small things can get through there. We're going to zoom in right here. And there we've done it. We've zoomed in. We've got blood on the left. We've got filtrate on the right. And we see only small stuff: water, glucose, amino acids, ions, urea, which is a waste product, hormones, vitamins, ketones, very small amounts of little proteins. Most proteins are too big, like albumin is too big, platelets, too big, white, red blood cells, too big. They cannot get through the little fenestrations or the little spaces between the feet of the podocytes. Well, there's the membrane for filtration. Let's talk about the forces involved. Now, we know there's blood in the glomerulus, and that blood is under high pressure, about 60 millimeters of mercury, and that pressure is pushing water out of the glomerulus into the filtrate. But it's not the only pressure that's involved here. The osmotic pressure of the blood, due primarily to albumin, is going to be sucking water back into the blood. So while we've got 60 millimeters of mercury pushing water out, we've got 32 sucking water back in. So we're left over with about 28 so far. But the filtrate, the water that ends up in the glomerular capsule, it'll try and push its way back into the blood with a force of about 18 millimeters of mercury. So overall, our net pressure for filtration is about 10 millimeters of mercury. And well, that's pretty high. That is definitely good enough. And that filtration pressure is really necessary because the filtration pressure, which is primarily due to glomerular blood pressure, is going to determine the glomerular filtration rate. In other words, how much filtrate do we make every minute? And we got to make about 125 milliliters a minute. It's got to be just that. If we make too much, filtrate will move too fast, and we won't have time for reabsorption. If we don't make it fast enough, and we make it too slowly, filtrate will move too slowly and will not only reabsorb the good normal stuff, sugars, vitamins, etc., but will start reabsorbing wastes, start reabsorbing bad stuff too. And if we look at it, I'm going to skip this graph, sorry. So to sum up, we got to maintain our glomerular filtration rate. That way we do the right amount of reabsorption and secretion, and we keep our urine and blood in homeostasis. To maintain glomerular filtration rate, we got to maintain glomerular blood pressure. And next time, guys, we'll talk about just how exactly we do that. See you later.